Welcome everyone. Project Supervisor Mr. Matabadal, Second Examiner Dr. Adianju, Moderator Dr. Manohar. A pleasant good morning. My name is Karen Dennis, and today I will be presenting on my final year project that of to develop a computational model to calculate gas turbine cycle performance. My agenda for today is to discuss the background and rationale for my project, aim and objectives, scope of my project, discuss the literature review and methodology, expected outcomes, and schedule of tasks to be completed. Now for some background on my project. When performing ideal cycle analysis on gas turbines, a constant mass flow rate is usually assumed for the working fluid throughout the cycle. As a result of such an assumption, the output performance from a real cycle will always be less than that from an ideal. The efficiency of the gas turbine is usually enhanced by increasing the turbine inlet temperature. However, this requires an increase in the flow rate of the cooling air, which can be as much as 20% of the compressor inlet airflow. Henceforth, a method is required to determine the actual output performance from the gas turbine. This leads to the aim of my project, that of to develop, analyze, and test a computational model and method that would predict gas turbine cycle performance when variable mass flow of cooling air is considered. My objectives for achieving this aim are to conduct a thorough literature review, to develop correlations between two cycle parameters, to create and test linear regression models, to improve and optimize this computational model, and to develop a series of performance curves. The scope of my project is to discuss the need for cooling air throughout the gas turbine designs, to differentiate between ideal and real cycle analysis, to justify the differences in the performances obtained from both cycles, and to discuss the need of a model that would be able to predict these output performance parameters. Moving on to my literature review. Bleed air is air that is extracted from the compressor stages, bypasses the combustion chamber, hence taking another route towards the turbine where it then mixes with the product gases following combustion. This blend of air at a much lower temperature creates a film of cooler air around the turbine blades. Now, the reasons why engineers found it necessary to use this bleed air concept in their designs are due to the fact that the bleed air acts as a coolant for the turbine blades and nozzles, thus reducing the thermal stresses on these components and hence increasing their lifespan. Also, it allows the gas turbine to operate at much higher turbine inlet temperatures, which leads to an increase in the output performance from the system. Moving on to the various methods by which turbine blade cooling can be achieved. Firstly, the air extracted from the compressor can be cooled in an evaporator pre-cooler by water injection before it is directed towards the turbine. Secondly, steam can be implemented as the coolant for the turbine. However, this method is only applicable for gas turbines designed specifically for combined cycles. And lastly, the air extracted from the compressor can be used to cool the turbine directly, and this is the method utilized within my project. On the basis of my project, it is imperative for one to be able to distinguish between real and ideal cycle analysis by analyzing and comparing the various assumptions and simplifications that are made in an ideal cycle analysis. Herefore, one can now understand that in reality, various losses and inefficiencies need to be considered when performing cycle analysis. Just to highlight some of the main differences between ideal and real cycles, in an ideal cycle, fuel and cooling air flows are negligible, whereas in a real cycle, they are accounted for. In an ideal cycle, the compressor and turbines have 100% efficiencies, whereas in a real cycle, the compressor and turbine are not 100% efficient. In an ideal cycle, pressure losses are negligible, whereas in a real cycle, they are accounted for. And in an ideal cycle, the turbine is uncooled, whereas in a real cycle, up to 20% of cooling air can be utilized. To emphasize on the inefficiencies of the compressor and turbine, we can see from the following TS diagrams the differences in the processes of compression and expansion. For the ideal cycle, we have isentropic compression followed by isentropic expansion, which indicates 100% efficiencies. For the real cycle, however, we have irreversibilities occurring, thus leading to an increase in entropy. Hence, the compressor requires more work to compress the working fluid, and the turbine produces less work as a result of expansion of the working fluid. Furthermore, reasons why a computational model is required are due to the fact that manufacturers do not provide relevant data to their clients, and also due to the various assumptions that are made throughout cycle analysis, which results in inaccurate performance data. Hence, a mathematical model that would take these various considerations into account would be very beneficial when performing cycle analysis. Through research and review, I was able to come across an article where Boeing had developed a gas turbine which did not incorporate any cooling air. This system, they claimed, would reduce fuel consumption, weight of the engine, and many more advantages. However, this proved to be a very costly project due to the implementation of stronger and higher heat-resistant materials. Furthermore, Zelko Caluso was able to develop a thermodynamic model that would utilize heat transfer data and implement them in turbine calculations for industrial and aero engines. This model considered the losses of turbines associated with the second law of thermodynamics, such as exergy, fluid mixing, etc. This model was validated through experimental analysis to produce fairly accurate results when compared to data obtained from ideal analysis. In contrast, Andrea Lazzaretto had created a model that would predict the off-design behavior of the gas turbine. This model aimed at simplicity, only analyzing a single cooling airstream from the compressor exit to the first turbine nozzle row. It was designed based on previous work done by Sue and Sarah Vanamato, where they were incapable of modeling the turbine cooling system accurately. Furthermore, with continued research, insufficient evidence was provided from this model for it to accurately predict the performance of the turbine due to various assumptions and simplicities implemented. In addition, Horlock et al. Was able to establish a method for determining the amount of cooling air required by the gas turbine. They developed two semi-empirical relationships between film blade cooling and pressure losses, which they use in calculations for the performance of the turbine subjected to varying combustion temperature and pressure ratios. Based on the results obtained from this method, D.T. Watson et al. Was able to suggest that for maximum plant efficiency, there would be a limiting combustion temperature and that the optimum pressure ratio is reduced by the effect of cooling air. Overall, based on the limited number of reviews and related articles found, dissimilarities and assumptions made in previous projects, and also that no model to predict cycle performance is currently available, there is great need for one to endeavor in this project. Onto my methodology. The procedure in which I intend to pursue this project is by researching and reviewing existing articles and projects, researching background information on gas turbine cycle theory, performing cycle analysis on various gas turbines based on data obtained from thermoflow, develop correlations between two cycle parameters and determine the strength of these correlations, implement these correlations to create linear regression models, examine the feasibility of the model by performing cycle calculations, compare the data obtained from the model to that obtained from an ideal cycle analysis, and to develop a series of performance curves. On completion of my project, my expectations are that an impeccable model would be created that is able to accurately predict the performance of any gas turbine, and that these predictions can be used to help improve and optimize gas turbine designs by many of the great manufacturers of gas turbines, such as General Electric, Mitsubishi, Siemens, etc., such that they can now design their turbines for any power output they so desire. This Gantt chart shows how I plan to carry out specific tasks in order to ensure that I complete my project on time. Highlighted in orange are tasks which have already been completed, and highlighted in purple are tasks which have yet to be fulfilled. That concludes my presentation for today. I thank you all for your time and attentiveness, and I will be happy to answer any questions which you may have. Thank you.